So the conical pendulum. So basically it sweeps out a cone. It's actually travelling in a horizontal circle, but obviously attached to a string, or in my case there's a bit of fishing line. But I was attempting to give it constant angular velocity. Let's put some dimensions in to help us out. So our cone, the string is going to make an angle with the vertical there. Obviously the circle has a radius, the cone will have a height. So we draw ourselves up a force diagram. There's good old Bob. So all the forces that are acting on Bob. Remember we said whenever a string is attached to an object, there'll be tension up the string, and that tension's always away from the object, so I know I've got a force going off in that direction. The only other force we've got really is gravity, so we've got mg as well. What it means is I'm going to break everything up into horizontal, that's vertical by the way, horizontal and vertical components. So we'll have a component of tension, because it's not completely vertical, it's not completely horizontal. Theta is the angle that we need, angular velocity, and so on. So we resolve our forces, as I say, in the horizontal direction and in the vertical direction. Now, horizontally, it's moving in a circle. So the resultant force must be equivalent to the centripetal force, mv squared on r, or mr omega squared, depending on what you're working with. Vertically, if I was spinning it right, so it was constant, it wasn't moving up or moving down, it stayed in a horizontal plane, and so nothing's happening there. So as far as the forces go, they balance out. So my double dot is equal to 0. So basically I start off with that idea. Horizontally I know all the forces will resolve to give mv squared on r, and vertically all the forces will resolve to give 0. Okay. So I'll draw myself up a little triangle so I can work out the components. So horizontally, the component of tension would be T sine theta, because we're opposite, and the sine would be opposite over hypotenuse, so opposite would be sine. And that's all, horizontally. Now, we know the resultant force in horizontal motion is always towards the centre. So therefore, that T sine theta, we can see it's going to the left or going to the centre, so it must be positive. So we get T sine theta would be equal to mv squared on r. Or, if you were using angular velocity, it would be mr omega squared. Now, vertically, we have a component of tension, but that one would be T cos theta, because it's the adjacent side. And we have mg as well. Now, because it's equal to 0, it really doesn't matter which one I make positive. I could make either. So I think I went with T cos theta. So T cos theta minus mg equals 0. I prefer to write it that way because it makes more sense. I do see some people straight away just go T cos theta equals mg, but I think you lose the problem, because what we're saying is these forces sum to give 0. It's a more logical starting point. So T cos theta minus mg equals 0, which means T cos theta equals mg. So now we can play around with these and discover some things. If I eliminate the tension, and I'll do that by division in this case, so T sine theta over T cos theta, that'll be mv squared on r divided by the mg. The m's cancel, and we get v squared on rg. So that's a way of working out the angle if I know the others, or if I know the angle I can work out the velocity or whatever. If I was using angular velocity, I would have ended up with r omega squared on g. Now, our triangle AOP. Remember we gave the cone some dimensions? So we can actually work out what tan theta is, and it would be the radius over the height. If I substitute that in, I get something a bit more interesting. V squared on rg is r over h. Playing around with that, I get h is r squared g over v squared. But if I do it in terms of angular velocity, I get something even better. G on omega squared. Now remember, g is a constant. Okay. So what is controlling the height of the pendulum is purely the angular velocity, because that's the only thing that's going to change. So what we're basically saying is our height is inversely proportional to the angular velocity squared. So the faster I go, the smaller the height will be. And that's why when I was spinning it, when I spun it faster, it rose, because the height of the pendulum got shorter. So these are the sorts of implications we can tell from that. So the depth of the pendulum is the technical term, so height of the cone, if you like, is totally independent of the length of the string, because it's only dependent on G and omega squared. Now, okay, there is a little dependence on the string, because obviously it's attached to the string and it can't go further than the length of the string. I mean, so there is that. But other than that, it's totally independent of the length. It doesn't matter how long my string is. If I spin it at a certain angular velocity, the height of the cone will always be that height. And as I say, as the speed increases, good old Bob rises. Okay, so let's use that idea. So the number of revolutions per minute, conical pendulum, we're going to increase it from 60 to 90 revolutions per minute. How far does our Bob rise? Now, if I'm starting from scratch, then I would resolve all the forces like I just did. So there's Bob. I've got tension going at an angle, mg going down. I'll need the R and H, that's going to help me out, and theta. But I'll resolve my forces. So horizontal forces, I know circular motion, so it'll resolve to be mv squared on R. Vertical forces will resolve to be 0. So it's pretty much exactly what I just did before. So T sine theta going to the left. So in this case, because we're dealing with angular velocity, I'm going to say mr omega squared. Vertically, it's still the same in that one. So T cos theta minus mg is equal to 0. And I'll come up with that equation again. So as I say, it's pretty much the same as I just did, but all I'm dealing with the angular velocity now instead of linear velocity. And so I get our r omega squared on g. But we know tan theta is r and h. So we come up with our formula for height. And so now it's just a substitution question. Once I've got this formula, h equals g on omega squared, I can say, well, when it was 60 revolutions per minute, but be careful. Angular velocity is not measured in revolutions per minute for the sake of this formula. It's got to be in radians. So I need to change that. Oh, how nice 60 works out to be. Oh, it's just 2 pi. 2 pi radians per second. That was lucky. So I'll sub it in. The height is g on 4 pi squared. And 90, oh, how lovely. It's 3 pi. So 90 revolutions per minute is 3 pi radians per second. So it'll be g on 9 pi squared. So the difference between the two must be how high it rose. 0.14. 0.14 is an approximation to the lift. All right, let's look at an HSC one. This is a nice one. The particle, there it is, good old Bob, is there. But there's just an added little complication on this. Not only is it a conical pendulum, it's sitting on a cone. All right, we've got a cone, a particle attached to a string, and it's attached directly above the vertex of the cone. And we're going to rotate it around the cone. It's going to roll around. Now, you'll notice there's some forces here. Yes, tension we're used to. They're N, normal force. Again, it's that resistive force. Whenever you make contact with the ground or a surface, there's a resistive force in the opposite direction. Remember, that's why I'm not falling through the floor at the moment. There's that resistive force balancing the gravity out. And that's what they've coded there. So normal reaction N and gravitational force. Okay? The normal force will always be, of course, perpendicular to the surface. So, show with the aid of a diagram that the vertical component of this normal force turns out to be N sine alpha. Okay, Bob. I have tension going up the string. So I'll need components of that. Based on their diagram, I can work out alpha would be in that position. We have a normal force going that way. Now, the question is, where is alpha in that diagram? So I've just got over here. Remember, alpha was the angle, the cone that it was sitting on. That one was alpha because of alternate angles. But then if I keep going with that triangle, remember we said the normal force was at right angles. So if that's alpha, that one in there is 90 minus alpha. Therefore alpha must be up the top there. Okay. So let's put that into our diagram. And we have gravity as well. It's just that vertical component that I've labelled C that we're trying to find. And so we can see, well, it's opposite the angle there. But, I mean, I can put an equation together so it's obvious where it came from. I can say, well, C over N would be sine alpha, so that component is N sine alpha. Show that the tension plus the normal force will be mg on sine alpha. So they've given us that one. We've got to work it out, of course. But in case we can't work it out, at least we've got that expression to work with. And find an expression for tension minus the normal force in terms of the mass, the length of the string, and the angular velocity. All right, well, the situation hasn't changed. Horizontally, it's still moving in a circle. So I'm going to use mr omega squared, seeing they've said they want it in terms of omega. And there's Bob. I'm going to have a component of the tension going left, but I'll have a component of the normal force going right. Okay. They will resolve to give mr omega squared. The positive direction will be towards the centre. So it's the t cos alpha that'll be positive. So we'll have t cos alpha minus n cos alpha is mr omega squared. All right, the vertical forces, they're going to sum to be 0. So what do we got? Let's draw a diagram. Component of tension going up, the normal force going up, gravity going down. And again, it equals 0, so it doesn't really matter in this case which one we make positive. So I've gone t sine alpha plus n sine alpha minus mg is equal to 0. And I'll move the mg over. Now, we want an expression for t plus n. Well, if you look at the right-hand side, it drops out quite nicely. You've got a common factor of sine alpha there. I can divide by sine alpha, and there it is. They wanted a similar expression for t minus n. If I now have a look at the left-hand side, we can do a similar thing. So t minus n, but of course they said put it in terms of not mr omega squared. But remember they said the length of the string they wanted it in terms of as well. So looking at our original diagram, the radius over the length of the string would be the cosine of alpha. So if I sub that in for r being L cos alpha, the cos alphas cancel. I get t minus n is ml omega squared for this question. And then asks us this question about the problem. So here we are, this conical pendulum rolling around on the cone. It's attached to the string. But we're going to increase the speed until the normal force is equal to 0. Now they've told us what happens there, but if you think about it, if there is no normal force, it means it can't be in contact with the cone. Because as long as it's in contact with the cone, there will be a normal force. So once it equals 0, it's lost contact. So we've sped it up, the bob's risen, and it's lost contact with the cone. So now they want an expression for angular velocity in terms of alpha, the length of the string, and g. So all right, we now know that the normal force is equal to 0. So we can change our equations. I know tension is mg on sine alpha according to my left-hand equation. But according to my right-hand equation, tension is ml omega squared. Well, it's the same tension. So I can say, well, mg on sine alpha must be ml omega squared, and I'll just make omega the subject of the formula. And there it is in all its glory. The square root of g on L sine alpha. So again, we'll take some out of our Cambridge and we'll take some out of, well, actually not some, we'll take all out of our Cambridge and we'll take all out of our Patel there.